Okay, so this morning we are going to continue our discussion of Newton's second law of motion, but we are going to be looking at the motion of an object or a box on an incline, which is something you will encounter in this course. Now, an incline is different from a flat horizontal surface because an incline is usually tilted at an angle. So an incline, this is an incline, this is a surface, then it is tilted at an angle theta like that. So what we want to study is how an object will move if it is placed on an incline like this. Are we clear about what an incline is supposed to be? So this is the incline. So it might be made of wood, or it might be made of concrete or something like that, but you've got something like this. And you want to study the movement of an object on this surface which is tilted at an angle theta. Are we clear on that? What an incline is? It's a tilted surface which makes an angle theta. Usually theta is less than 90 degrees. Are we clear?
Yes, sir.
Okay. So next, what we do is that we, on this particular incline, which makes an angle theta, we put an object or a box of mass m. So we put an object on top of this incline. So when you put something on an incline, there are a couple of things which are going to happen. Basically, there are basically two things which will happen. Either that particular object, so that particular box you have put on an incline, will stay stationary or stay motionless on the incline, or that particular box will move. And usually, if you have any experience with something moving on an incline, it starts off slowly, then its speed increases, and it moves faster and faster and faster. So basically, we are talking about two options here. Either the object on the incline remains motionless, meaning that there is no acceleration, or the object is going to accelerate under its own weight. Of course, there are other things you can do to make sure that this particular object goes down an incline at constant velocity, but that's not interesting. Okay, now for us to study why this particular object, if it decides to remain motionless, why does it remain motionless? The reason why it remains motionless is because there is no acceleration. That's the only reason why something remains motionless, because there is no acceleration. But the more important question is, why is there no acceleration? The reason is because the resultant force acting on this particular box is equals to 0. So there is an issue of resultant force being absent. So this is a case where the resultant forces actually add up to 0. So there are forces acting on this particular box. Okay, so in the case where the box is motionless, the acceleration is equals to 0. However, it has got mass. So the mass is not equals to 0. If the acceleration is equals to 0 from F is equals to ma, from Newton's second law of motion, F is equals to ma. If the acceleration is equals to 0, it is, and the mass of the box is not equals to 0, it means that the resultant force is equals to 0. So in that particular case, when the box decides to remain motionless, the resultant force adds up to 0. In the other case, the same box can also decide to move faster and faster down the incline. So if it's moving faster and faster, then it means that in that particular case, when it's moving faster and faster down the incline, sliding, it means that there is acceleration. So if there is acceleration as it is sliding down the incline, then it means that that acceleration is being caused by the presence of a resultant force, which is predominantly pointing downwards, because according to Newton's second law of motion, an object will only accelerate in the same direction as the resultant force. So if you see the velocity of an object, in this case, increasing downwards as the object slides downward, it means that the resultant force is pointing in that direction in which the velocity of the object is increasing. So we've got two interesting cases. The first case is when the object remains motionless, telling you that the resultant force is not absent, or it's there but it adds up to zero. Then you've got another case when the object's velocity increases. When the object's velocity increases, it means that the resultant force is present and it is not equal to zero. So there is need for us to find out what is the nature of the resultant force acting on this box. Are we clear? We need to find out the nature of the resultant force acting on this box. Is that clear?
Yes, sir.
Yes, because if at one point you have acceleration on the same box, then at the next point the box decides to move, slide down, then you start asking questions. Why is it not accelerating when it's motionless, and why is it accelerating when it's sliding? So there is one point, there is acceleration, the other point, there is no acceleration. The only way we can answer the why there is no acceleration when it's not moving and why there is acceleration when it's moving is to look at the nature of the resultant force. We know there's some acceleration at one point, we know there's no acceleration, but we know the mass. So the only thing we do not know is the resultant force. What does the resultant force look like in this case? Okay. So this job of looking for a resultant force will make us look for the forces which could possibly be acting on this box. What forces are acting on this box? There are two obvious forces acting on this box. If this box just stays there are two obvious forces. The first force is from the fact that this box has got mass. If this box has got mass, then it means that this box is being attracted towards the earth, towards the ground, by the earth. So this box has got weight. So any object near the surface of the earth which has got mass m has got a weight acting on it. It's being pulled down by the earth with a force of mg, mass times acceleration due to gravity. So there is a weight acting on this box which is pointing downwards, as you can see here. There is a weight acting on this box which is pointing downwards. The other thing, and the other force which is not obvious but is present, is something called friction. Friction is present when an object is not moving. Friction is present when an object is not moving. So even for a stationary object like this box has got friction. Naturally, on an incline, this box on its own, if you don't do anything to it, it would like to move down the incline like this. Okay, it would like to move down the incline like that. That's what things do. However, because of friction, which is going to oppose the movement of this box, the friction will be acting upwards, the incline. So the friction will oppose the movement of the box down the incline. So the other force which is present in the movement of this box is friction, which is pointing up the incline. So there is friction and there is weight. So the friction is pointing up the incline, the weight is pointing down this way. Then how does that explain our calculation of resultant force? For us to calculate resultant forces, we need directions. So in this case, there are two directions which we are going to choose. We are going to choose the direction which is along the incline. So the direction which is along the incline or parallel to the incline, that is what we are going to choose to be our horizontal direction. So along the incline or parallel to the incline, we're going to choose that as our horizontal direction. In other words, I am saying that along the incline, that is what we are going to choose as our x-axis. So along the incline, that will be our x-axis or horizontal direction. Then parallel to the incline, not parallel, at 90, perpendicular to the incline, at 90 degrees to the incline, that is what we're going to choose as our y direction. So whenever you have a surface along the incline or parallel to the incline, that is your x-axis. Then at 90 degrees to the incline, that is your y-axis. So that is the choice of direction we make. So we choose the direction which is along the incline or parallel to the incline to be our x-axis. Then we choose the direction which is perpendicular to the incline at 90 degrees to the incline to be our y-axis. Next, after you choose your x and y axis, this x and y axis choice is not complete, because remember, we have to choose which one is the positive x-axis and which one is the negative x-axis if we are going to work out resultant forces. Now, along the incline, what is going to help you is the direction in which the mass is moving, or the direction in which the mass tends to move. If, in our case here, if this box slides, it is not going to slide up, it will slide down. So the natural direction in which an object tends to move or slide can be chosen as the positive x direction. The reason why we are choosing it as a positive x direction is because the acceleration is increasing, will increase in that direction. So we want to have a positive acceleration in that direction. As the velocity increases, it means that the acceleration will increase in that direction. So if an object is moving in a particular direction, you can choose the direction in which the object is moving to be the positive x-axis, and that is what we do in this case. So we choose the downward direction, downward horizontal direction along the incline to be our positive x-axis. Then we choose the upward horizontal direction, which is opposite the direction in which the box is going to move, to be our negative x direction. So if we choose the downward direction to be the positive x-axis, then the opposite is going to be the negative x-axis. Are we clear on that? You are using the direction in which the velocity of this particular object is going to increase, or the direction in which the object is moving, to be your positive direction. Are we clear? So we are trying to put an XY plane on this incline. Okay. Any questions on what we're deciding? So after deciding to say our horizontal direction, which is the x-axis, downwards is going to be positive x-axis and upwards is going to be negative x-axis, then we come to a choice of positive y-axis and negative y-axis. So in that case, we have said perpendicular to the incline, that's going to be our y-axis. So at 90 degrees to the incline, that will be our y-axis. Now, that is not enough. So we make another choice, say above the incline, that will be our positive y-axis, and below the incline, that will be our negative y-axis. So in this case, with our xy plane complete, where we have with the positive x-axis downwards, the negative x-axis upwards, the positive y-axis above the incline, the negative y-axis below the incline, our xy plane is complete. However, something becomes very evident if you're going to use this kind of xy plane, one which is parallel to the incline for the x-axis and perpendicular to the incline to the y-axis. It becomes apparent that the weight of the box, which is this one pointing downwards, neither points along the x-axis nor the y-axis. That is what becomes very apparent. With this choice of axis, it becomes evident that the weight of this box does not point along the x-axis, it does not point along the y-axis. However, there is a portion of this weight, there is a fraction of this weight which points along, which lies along the x-axis. There is also a small amount of this weight which lies along the y-axis. The amount of the weight which lies along the x-axis, that is what we call the x component of the weight in this case, and the amount of the weight which lies along the y-axis, that is what we call the y component of the weight. So in this case, how much of this weight lies along the x-axis or is parallel to the incline is given by this component here, the mg sine theta. So you have got this thing here, like that. This is your m. Then, since we have chosen parallel, perpendicular to the incline to be our y-axis, like this, so you're going to end up having this line here being a y-axis. So this mg cos theta lying along your y-axis, and you're going to make an angle between the weight mg and the y-axis. That angle between the weight and the y-axis is also equals to the angle of the incline, this theta here. So this theta, which is the angle of the incline, also turns out to be geometrically equal to the angle between the weight of the box and the y-axis. So if this vector mg makes an angle theta with the y-axis, then you can find out using your trigonometric sine and cosine for a right angled triangle. You can find out that the adjacent of this little triangle you have created, which is a triangle of components, the adjacent here is going to be mg cos theta, and the opposite this side is going to be mg sin theta. The thing about the opposite component here, which is also a vector, it's dotted like that. The dotted means that it is a component. This component, which is mg sin theta, and there's an arrow at the end, meaning that this component is a vector. So components are also vectors, in that as much as we know their size, they are vectors because we know the specific direction in which they are pointing. We know precisely in which direction this component is pointing. So as you can see, this component here, which is mg sin theta, lies parallel to this incline. It's parallel to this incline. So the direction of the component is in the same direction as our choice of x-axis. So this mg sin theta becomes the x component of the weight. Then this one here, mg cos theta, lies along the y-axis. So this mg cos theta becomes the y component of the weight. Are we clear? So now in this case, in an incline, your components have changed. Naturally, when you're on a flat surface and you're working out components, your x component is mg, is whatever the force is, or the vector is, cos theta, or the other thing, sin theta. So in this case, you have a different thing. I've lost internet. Just a minute.
Yes, we can see.
Okay, so this is what we have in terms of the weight. Because of our choice of x-axis, by choosing our x-axis to be parallel to the incline and pointing downwards as positive x and upwards as positive y, and perpendicular to the incline to be our y-axis, above the incline to be positive y, below the incline to be negative y, we come to the realization that the weight of our box lies neither along the x-axis nor along the y-axis. So if the weight lies neither along the x-axis or along the y-axis, it will be difficult for us to find out the resultant force, because we need to find the resultant force along the x-axis. We also need to find the resultant force along the y-axis. So we find out how much this weight is along the x-axis and how much this weight is along the y-axis. And this triangle, these vectors, components under this vector mg sin theta gives us the x component of the weight, and mg sin theta, this mg sin theta gives us the x component of the weight, and mg cos theta gives us the y component of the weight. So you notice that mg sin theta is pointing downwards. So mg cos theta pointing downwards is telling us that this component, with the choice of xy plane we have, is a positive component. Okay? Then mg cos theta is pointing downwards again along the y-axis. So downward, we have said below the incline is going to be negative y. Above the incline is going to be positive y. So below the incline, we are going to have mg cos theta, which is going to be negative force. Now, this mg sin theta also explains something. It explains the reason why an object on an incline tends to move downwards. It is because, depending on the weight of the object and how the incline is, this mg sin theta depends on the weight. So if the weight of the object is large, then mg sin theta is going to be large, meaning that there is going to be a force, mg sin theta, pulling the box down the incline. That's why the box tends to move down the incline. The box does not move up the incline because usually friction is very little. Are we clear? So this mg sin theta is the force, is the part of the weight that tends to pull the box down the incline. That's why something along on an incline will tend to move down. It's because it's being pulled by this mg sin theta. Okay? On the part of the friction, if the box is being pulled down, the friction is going to be opposite. That's what the friction is going to be. The friction is going to be opposite, and usually in most cases, friction is very small. So these are the only two forces acting along the x-axis on this particular box. There is mg sin theta pointing downwards, then there's friction force pointing opposite direction. So the mg sin theta and the friction force will have to fight it out. It is out. So if mg sin theta is equal to the friction force, that explains why there is no acceleration. But if mg sin theta is greater than the friction force, it means that a resultant force is going to be present and the box is going to move down. The other thing which happens is this mg cos theta. This mg cos theta is the component of the weight which is exerted directly on the incline in the direction of at 90 degrees to the incline, like this. This mg cos theta. The incline is not going to be happy about this. So the incline is going to react and it's going to push back with an equal but opposite force. That is what we call the normal force. Okay, so let's have a look at a better diagram with our forces which have come up with represented properly. So here we have our box. Now with this box, now we have this force which was down here, which is mg sin theta. We have lifted this mg sin theta, we have brought it near the box like that. The reason why we can do that is because mg sin theta, as you can see, it has dashed lines and it has got an arrow at the end. It is a vector. If something is a vector, it means that you can lift it and put it in a different position as long as the size of the vector has not changed, and also as long as the direction in which the vector is pointing remains unchanged. So when I get this vector, I put it here as it has been done here. We lifted it from down here, we put it there. The size of the vector is still mg sine theta. The direction in which the vector is pointing is still the same. It is still parallel to the incline. So in that case, if the vector is still parallel to the incline, then the vector is the same and it has not changed. That's the one thing you can do with vectors. You can lift them and put them in more suitable places so that you can see the directions in which the vectors are acting. So as you can see here, along the y-axis, along the x-axis, pointing downwards, there is this component of the weight, which is mg sine theta. Then directly below, downwards, that's a weight. But because of the choice of axis we've made, the weight neither points along the x and the y. That is what has made us to look for this mg sine theta. Then down here, you've got the mg cos theta, which is the y component of the weight when you're on an incline. This mg sine theta is the one which tends to pull the box down. So if the box is going to move down, there's going to be motion, whether it's stationary or it's moving. There's going to be friction to oppose the motion of the box. And that friction force is going to point upwards, which is what this F is showing here, small f. That is the friction force. Okay, so if the box is stationary and the box has got weight, it does not mean that there is no force acting on it. No, the mg sine theta is still there. Okay, it just happens that when the box is not moving, mg sine theta is equals to the friction force. So there is no resultant force along the x-axis. Okay, next there is this component which is mg cos theta, which is pushing against the box and against the incline, and the incline is not happy, so the incline pushes back with the normal force like this. So in our case here, we have identified this component along the x-axis pointing downwards. There's a friction force opposing that component. There is a y component of the weight pushing downwards against the incline. The incline is not happy about being pushed around, so the incline pushes back with a normal force like that. Are we clear on how we have arrived here? Is it clear? Before I proceed? Okay. Next, now we need to work out the resultant force. We start with the resultant force along the y direction. It's very simple because the box only moves along the x-axis, along the incline. So the position of the box along the y direction does not change. If the position of the box does not change, the velocity of the box along the y direction does not change, it means that there is no acceleration along the y direction. So along the y direction, we want to find the resultant force. So the forces acting in the y direction is this one, the normal force N, and the mg cos theta, which is the x component. We have said above the incline is going to be positive, below the incline is going to be negative. So the resultant force along the y direction is going to be equal to the normal force plus the component of the weight pointing along the y direction, which is mg cos theta, and since it's pointing down, we give it a negative sign. So we end up having the resultant force along the y direction being equals to Fn minus mg cos theta like this. Since there is no acceleration, then we write Newton's second law of motion, which is this. The resultant force along the y direction is equals to m, the mass of the box, multiplied by the acceleration along the y direction. Since there is no acceleration along the y direction, since the acceleration along the y direction is equals to 0, then when you multiply this mass multiplied by the acceleration of 0, you get 0 this side. So you end up having 0 on this side. But this side, your resultant force, the sum of the forces along the y, is the normal force minus mg cos theta. That's what you have here. So you have normal force minus mg cos theta this side equals to 0 that side. So this Fn minus mg cos theta, you get this part to the other side, you end up having the normal force being equals to mg cos theta like that. So the normal force with which this box pushes back against, with which the incline pushes back against the box, is equals to the y component of the weight. So the normal force Fn is equals to mg cos theta. That's what we get from applying Newton's second law of motion along on the box along the y direction. So you end up having Fn, which is the normal force, is equals to mg cos theta. So that's all we can do along the y direction. Then we turn our attention to what's happening along the x direction. So along the x direction, we have said coming down this way is a positive x direction, up is a negative x direction. So this force mg sin theta is positive, that friction force is going to be negative. So the x component, so the resultant force along the x direction is going to be the mg sin theta, which is positive, plus the friction force, which is this one, but the friction force is pointing in the negative x direction, so it's going to be like that. So our resultant force along the x direction is going to be mg sin theta minus the friction force. However, we know that friction is always expressed in terms of the coefficient of friction and the normal force. This one, friction is always equals to the coefficient of friction times the normal force. So in that case, instead of writing friction there, we substitute that with coefficient of friction multiplied by the normal force, like that. So our resultant force along the x direction becomes mg sin theta minus the coefficient of friction multiplied by the normal force. Now that we have the resultant force, which is this one, equation number 9, we can also apply Newton's second law of motion along the x direction. So along the x direction, we have the resultant force, then the mass of the box, and the acceleration. So there are two things, as we have said, which can happen along the x direction. Either the box can remain motionless, it decides not to move. When the box remains motionless, it means that the acceleration is equal to 0, or the box can slide down the incline and move faster. So in that case, the acceleration is not equal to 0. So we're going to look at the first case where the box remains motionless and the acceleration is equal to 0. So in that case, when the box remains motionless, ax is going to be equal to 0. So when you do that, you end up having whatever the resultant force is equals to multiplied by the mass times the acceleration of 0, that is going to give you 0. Because the box has remained motionless, the friction acting on the box, this friction becomes the static friction force. So we end up having the resultant force, the sum of the force along the x, as mg sin theta minus the coefficient of static friction multiplied by the normal force equals to 0. So what we end up having here is, when you take this to the other side, you end up having mg sin theta equals to mu s, which is the coefficient of static friction multiplied by the normal force. However, if you recall, we have already found an expression of this guy, normal force along the incline. When you are on an incline, your normal force Fn is equals to mg cos theta. So we substitute for that in this expression here. When we substitute, we end up having mg sin theta equals to the coefficient of static friction, mg cos theta. So we have mg sin theta this side equals to coefficient of static friction, mg cos theta, like this side. Then we divide both sides by mg cos theta. When you do that, you end up having the coefficient of friction, static friction, is equals to mg sin theta on top divided by mg cos theta at the bottom, which is going to the mg and mg will cancel out. So you end up having sin theta divided by cos theta, which gives you tan theta. So in this case, when your box decides not to move on an incline, the first thing it means is that mg sin theta is equals to the friction force. That's the first thing it means. When your box remains motionless on an incline, the first thing it means is that the x component of the weight, which is mg sin theta, is equals to the friction force, mu s Fn. Okay, that's what it is. So if that is the case, we know how to find Fn. We want to what is the static friction force in this case. So that static friction force, so the coefficient of static friction is just found by getting the tangent of the incline. That is what the friction is going to be. And if you know what the static friction force is, then you can find the angle of the incline, which is equal to the tan inverse of the static friction, or the arctangent of static friction, like that. Are we clear on what happens if the box decides not to move? So if the box decides not to move, then the x component of the weight, the force or the component of the weight pulling the box downwards will be equal to the static friction force. And from that, you can find out that actually the coefficient of static friction is equal to the tangent of the incline. The other case which can happen, since I'm not receiving any feedback whether people have understood or not, the other thing which can happen is that the box can decide to slide. Now, if you have any experience about going down an incline, you notice that you cannot move at constant speed on an incline. Your speed is going to increase. As you go down the mountain, your speed will always increase and increase and increase. That's what's going to happen. So in this case, the acceleration is not equal to 0. Okay, so in that case, if the acceleration is not equal to 0, we can apply Newton's second law of motion, since we have got an expression, of coefficient, of resultant force. Just a minute. Someone else wants to teach. Just a minute. Okay, so if the velocity of the object is going to increase, then you are obligated to find out what the acceleration is. The fact that the velocity of the object is increasing tells you that the acceleration is not equal to 0. Otherwise, the only time acceleration is equal to 0 is if the velocity of the object is equal to 0 or the velocity of the object is constant. So in this case, as your object slides down the incline, its velocity will increase. That tells you that there is acceleration. And if there is acceleration, you are under obligation to find out how much the acceleration is. Okay, so in this case, we know the mass of the box. We are trying to find the acceleration. We know the resultant force. Along the x direction, it's always mg sin theta, which is the x component of the weight minus the friction force. So in this case, because our box is sliding, then this part is moving, so this coefficient becomes equals to okay. So like I was saying, because the object is moving, then the coefficient of friction in this case is going to be kinetic, and the type of friction which is going to be present is going to be kinetic friction. So in this case, we're going to end up having the resultant force as mg sin theta minus mu k multiplied by Fn equals to the mass multiplied by the acceleration. So what you're looking for here, we have this expression for Fn. So this expression for Fn, when you substitute it, you end up having this. You end up having mg sin theta minus mu k mg cos theta equals to ma. So what you're looking for is the acceleration. What would the acceleration look like? So you divide both sides by m. When you do that, you end up having ax is equals to mg sin theta minus mu k mg cos theta divided by m. Then you spread out the m, so you end up having mg sin theta divided by m this side. Then you end up having mu k mg cos theta divided by m. So you divide m on both sides, you end up having ax is equals to g sin theta minus mu k g cos theta. So there's a g this side, there's a g that side. You factor out the g, you end up having the acceleration ax equals to g, then open bracket sin theta minus mu k cos theta. So this is what the acceleration is going to look like when that particular box slides on an incline. So this is a general form of the acceleration when your box is sliding along the incline. So with this expression of acceleration, we can use this expression in different ways. For example, if you assume that your box is sliding on a frictionless surface, meaning that this surface is so smooth that there is no friction. If there is no friction, then the coefficient of kinetic friction is going to be equal to 0. If the coefficient of kinetic friction becomes equal to 0, then this part is going to be 0. Then this second part here is going to disappear because you're going to have 0 multiplied by cos. So when you've got 0 multiplied by cos, the acceleration in that case of the box is going to be equal to just g sine theta. So this is going to be the form of the acceleration as g cos theta. On the other hand, if your incline becomes horizontal, it becomes flat, so you're saying you're changing the angle of the incline from whatever it is to 0 degrees, so you make your incline become flat. So this angle theta, if this angle theta becomes 0, so basically your incline becomes flat. If theta becomes 0, then a couple of things are going to happen. So you're going to end up having ax is going to be equal to g, then sine 0 degrees minus mu k cos 0 degrees. So in this case, sine 0 degrees is equals to 0. Then cos 0 degrees is equals to 1. Okay, so sine 0 degrees is equals to 0. Cos 0 degrees is equals to 1. So in that case, you end up having ax, which is the acceleration of an object on a flat surface moving on its own. Basically, this is a case of sliding, is equals to the coefficient of kinetic friction multiplied by g. This coefficient of friction multiplied by g. So this is what the acceleration becomes if your incline turns out to be a flat surface. Okay, so if your incline goes back to being a flat surface, then in that case the acceleration is just going to be equals to a result of the coefficient of kinetic friction multiplied by g, and it's going to be negative. Okay. In the other case where the incline, you increase the incline, the angle of the incline, and the angle of the incline becomes equal to 90 degrees. If the angle of the incline becomes equal to 90 degrees, then the acceleration ax in that case is going to be equal to g sine 90 degrees minus mu k cos 90 degrees. Now sine 90 degrees is equal to 1, cos 90 degrees is equal to 0. So 0 multiplied by whatever the coefficient is, that will give you 0. So you end up having remaining only with g multiplied by 1, and that gives you an acceleration ax, which is equal to g. So when you have an incline which becomes a wall, a vertical wall, the acceleration in that case is just equal to the acceleration due to gravity. Any questions? We have reached the end of this topic. Any questions on the acceleration, on the motion of a box along an inclined plane? Okay, if there are no questions, then we come to the end here. Thank you very much. See you next week. Oh, I've just noticed that my mic was mute. Alright, there's a recording of this thing, so you can just watch the last part of the recording. I can't really go back because there are other things which I have to attend to right now. Okay, so see you next week. The recorded thing will be posted on YouTube.